For those of you who don't know me, my name is Jun Nogami. I'm the chair of the Materials Science and Engineering Department. And it is my pleasure to welcome all of you here, faculty and staff, students, as well as alumni and friends of our department, to MSE 100, which is the celebration of the centennial of the founding of our department and a celebration of 100 years of materials innovation at U of T. We have lots of events planned for this today and tomorrow, and to kick off this two-day affair, we have the first of two Winegard lectures, which are made possible by a generous bequest from alumnus Bill Winegard, who will be with us here tomorrow. Today's lecture is going to be a more technical lecture, whereas tomorrow's lecture will be a public lecture. Bill Winegard's vision for this lecture series comes from his memories as a student when he was here, and the department would bring world-famous leading materials scientists through the department to give talks and to lead discussions. And we are very fortunate today to have one such leading materials scientist with us here today. Michael Ashby is the Royal Society Research Professor Emeritus of Materials Science and Engineering and the Principal Investigator of the Engineering Design Center at Cambridge University. Professor Ashby is known certainly to all of our students. He's the father of materials selection, and the use of what's called the Ashby plot is a cornerstone in both the teaching and the practice of materials science and engineering. Professor Ashby has published over 200 papers and many other publications and books ranging from a manual titled How to Write a Paper, which should be required reading for all the graduate students in the audience, to some of the standard textbooks on material selection. He is also one of the co-founders of Granta Design, which publishes the CES material selection software that is used in our department and as he told me this morning, in thousands of other MSE departments worldwide and with wide application in the industry as well. Among his numerous honors and awards, he is most notably a Fellow of the Royal Academy of Engineering, a Fellow of the Royal Society, and a Commander of the Most Excellent Order of the British Empire. Ladies and gentlemen, I give you Michael Ashby.
Well, good morning, everybody. I'm very pleased to be here on this auspicious occasion, the 100th anniversary of the department. That must make it one of the oldest materials departments in Canada and one of the oldest in Europe as well. The material science is a comparatively young subject. And I'm going to start my talk with a little bit of history, which bears on that. Well, here's where we started. A long time ago, there's a man trying to make a bit of heat, and out of that grew some tradition and some empiricism, and we rolled that up and we called that metallurgy. And here's metallurgy. Here we are at the beginning, about the time I was an undergraduate, really, metallurgy. But then we began adding other things to metallurgy, and in the end, around the 1970s and 80s, we rolled that up and called it material science. And then we began adding even more things, composite science and that sort of thing, and engaging between materials and design, structures, that sort of thing. Not many of us worry about the economics of materials, but we should, and that began to appear in there. So we are today wrapping that up yet further. Now, what's the package we're wrapping it into? Here's one direction we're going, the nano, and there's a panel discussion tomorrow about nanostructured materials. So that's going down in scale. But we are also going up in scale. There's a number of things associated with materials which are of global reach. One is the resources from which we draw them. They come from all over the world. One is the way that we then use them, manufacture all over the world. And another, of course, is the impact they have on us, the emissions and the other things which also permeate all the way around the world. Most notably, things like global warming, possibly climate change. We perhaps don't yet know, but we suspect. And so we have to begin to think, instead of material systems and design, in this evolution of the way our subject's going. Well, what do I mean by material systems and design? I'm thinking of things like sustainability and the environment and economics and the legal side of materials and even the social impacts of materials. So that's the bit that we're either in or heading towards, and one large and clearly global aspect of that is sustainability, and that's what I'm going to talk about today. So that is by way of introduction. Now, discussing sustainability, and particularly in a materials context, is not simple. It involves materials, it involves energy, it involves some other things too, and I'll introduce the other things with two pictures. Here's one. If you want possibly the most energy efficient per passenger mile mode of transport in the world, and maybe even a materials efficient mode of transport in the world, it's probably that. But there could be safety issues. It might not be legal. It might not even be socially acceptable everywhere. So is it sustainable? Well, as a general mode of public transport, probably not. We don't do it that way in the West, we do it this way. It's legal, it's socially acceptable, it's fairly safe, but it does have its problems. It uses a great deal of material, it burns a lot of energy, it takes up a lot of space, there's emissions involved in that, and it's expensive. If you own a car, you know that. Well, I've just described two aspects of sustainability. I should add, even car companies, even the makers of cars, begin to wonder whether that is a sustainable mode of transport into the future. Well, let's just think for a moment of the words I've used in about 2 minutes to describe two aspects of sustainable transport. Here they are. Energy, materials, environment, emissions, safety, legality, social acceptance, space, economics. Actually, there were more. So as you can see, sustainability is not a simple issue. It's not just, is it green? It's more than that, much more than that. So how are we going to come to grips with it? Well, here's the mission statement, so to speak. Provide a framework within which a student, or anybody else for that matter, can form a critical independent assessment of something called a sustainable development. And I'll show you a list of proposed sustainable developments in just a moment. Starting point for any issue, any discussion of sustainability has to be this thing that I'm sure every one of you has read before. I'll read it in all the same. Sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. That's the Brundtland Committee back in 1987. Much quoted. You can't argue with that. But there is the question of how. What are we going to do about it? And as material scientists, how are we going to deal with that? Where do materials fit in? Now, I'm going to draw a distinction before I go on between sustainable or sustainability and sustainable development. Something that's sustainable will last. Something which is not sustainable won't. So it's an absolute term. Sustainable development is a relative term. Sustainable development is a development which moves us from something which is slightly less sustainable to something which we believe at the time is slightly more sustainable. Well, it's almost impossible to assess whether something is ultimately sustainable, but it is possible to assess whether a development is, given the knowledge we currently have, whether a particular enterprise or project is a sustainable development, and that's what this talks about. Well, the way that business thinks of it is the familiar triple bottom line. I'm sure you've all seen that. Planet, prosperity, people. You'd like to behave in a way or manufacture goods or use materials in a way that is not damaging to the planet. It generates disposable income, and in every other way is fair and to people and provides a livable environment, and the little sweet spot is the bit in the middle, which is the sustainable bit. Well, that's much used as a model in industry, and corporate sustainability reporting involves reporting a financial bottom line, that's that one, a social and ethical performance bottom line, that's that one, and an environmental performance bottom line, that's that one. So a company that has, let's say, an operating profit and has provided additional training for its staff and has perhaps improved its recycling record a little bit, can claim to have a positive triple bottom line, that they can do that. And indeed, there are indices, there are 4 or 5 of them. The Dow Jones Sustainability Index is one of them, which measures exactly those things. And says that company has a good record and a high index on our way of reckoning. But if you're a materials scientist or an engineer, it's not quite so clear what this is telling you. What can we do? What sort of materials science is going to bring us into here? Well, the way to approach that is to decouple these 3 circles. They may not, after all, ever overlap completely. It's rather hard to see how you can do that one and that one without using resources from this one. So whether there's ever a total overlap is not entirely clear. So let's pull them apart and see what's inside them. Well, here is a slightly different point of view. Still 3 circles, still with the same general meaning, but it's more a macroeconomic view. Natural capital, there are 3 capitals that one can see as having, as being important in the way that we reckon up the way we live. Natural capital, that is atmosphere, land, fresh water, oceans, biosphere, and of course material and energy resources, the resources from which we draw our materials. There is manufactured capital, that was the prosperity bubble. Well, the built environment is manufactured capital. This university is natural capital. Not the intellectual content, I'm talking about the buildings and the infrastructure. There is things like the financial health of the country, the GDP of the country. That is all manufactured and financial capital. And then finally, there is human and social capital, and that includes what goes on in this university: education, healthcare, skills, knowledge, happiness, and that kind of thing. Well, that is a slightly better way of looking at these things, or at least a slightly more detailed way of looking at these things that we can begin to come to grips with. And people like to think, or economists like to think, of wrapping these up and thinking of the comprehensive capital, which if you could attach a dollar value to each one of these, and they do try to do that, if you could attach a dollar value to each one of these, what the comprehensive capital measures is whether the sum of the 3 is positive or negative. So that at least gives you latitude to say, well, we may have to use some resources from the planet, but if it generates intellectual knowledge, better ability to recycle or use things or find new ways of doing things, then it may be justified to use a resource in order to compensate down here. You can see the picture. So sustainable development in this picture, at least to some people, is a growth not in each one of these separately, but in comprehensive capital. Right. Still a bit hard to link that to the research that we do in a place like this. So let's get down to that level, to the research level, the sort of things that you find in the headings of papers in the journals that we read. There are many such proposals, and I'm going to call them by this rather odd word, articulations. They're articulations of sustainable development. They're statements that claim that, if implemented, would move us from a slightly less sustainable to a slightly more sustainable position. So remember that word, because I'm going to be using it to mean exactly that. Here's an articulation: biopolymers. Should we be putting a lot of effort into replacing oil-based polymers by biopolymers? Well, there's a motivation behind that, an environmental motivation, which is to reduce our dependence on oil, and I'm going to call that the prime objective of that articulation. And that phrase will come up again in a minute. But almost always, articulations of sustainable development have unintended consequences, and one here is that if you're going to use land to grow the feedstock to make the biopolymers, then you're going to have less land to grow food on, and that is a problem. That's a genuine problem. Here's another one: carbon taxes. The idea there is to stimulate a low-carbon economy, but you can't tax carbon without increasing energy price somewhat, because that's at the moment where we get most of our energy from. Design for recycling. Well, that's a wonderful thing to do. It stimulates a circular materials economy, and there's a lot of discussion, at least in Europe these days, of circular materials economies. But it does have the problem that it inhibits the use of materials that can't easily be recycled, like CFRP or other composites. So I give you these three examples, and I'm going to show you another 27 in a minute, not quite like this, but in a different format, to bring out the following point, that each prime objective, each articulation has a prime objective. Here they are. There was a motive. They thought they could do something. But very often they have unintended consequences, and the unintended consequences are sometimes that one articulation, which has a very good motive behind it, actually clashes with another one. So the picture is very complicated, and that's the problem we've got to face. Well, before I go back to more articulations, I want to move on and then come back to those in just a minute for the following reason, that any articulation has stakeholders, people who are affected by it or are interested in it. The first task we have to find, if we're looking at one of these articulations, is who are they? What are their concerns? What are they worried about? And what power do they have? If they've got concerns, what are they going to do about it? Well, here are some possible stakeholders in any one of a number of different such articulations, you might say. Government, the public, local communities, the owners of a business, the manufacturers of products, the suppliers, the trade unions, customers, lobbyists like green activists, investors, of course, national press, managers, the general public. You can think of more. There's a great long list like that. It's quite nice to have a checklist when you're doing these kind of assessments because it at least reminds you of the questions to ask. Well, supposing we had an articulation, I won't say what it is, and these four characters here were seen by us as important stakeholders, then it's very important to find what their concerns are, because if their concerns are not met, the articulation is unlikely to be a sustainable development. They're going to stop it happening, and that means it isn't a sustainable development. So before you go any further with one of these articulations, you have to find out who's affected by it. And once you've got that information, you can plot a stakeholder diagram, and here it is. It's got the interest, how interested are these people in the thing you're proposing, and how much influence have they got to affect it. Can they hold it up? Can they make it change? Are they going to be a problem? Are they going to be an ally? That sort of thing. And you can begin to put these people onto this diagram like that. Here are the people who are really interested and have a lot of power, and here are the people who maybe are interested, well, they don't have much interest and they don't have much power at all. And you can then examine how they interact with each other. So if this one tries to influence that one, you might worry about this one or even this one, because they have very little influence of their own, but if they can influence others, they can acquire influence through others. And so pictures like this are really quite useful because they tell you that the things that end up in this box up here are the ones you've really got to worry about. So remember that, it's a kind of layer. I've made a planar layer out of these things here. And the advantage of making layers, which I'm going to emphasize in a minute, is you can begin to see how things interact with each other. And here, in this diagram, I'm sort of showing schematically how the stakeholders interact with each other. Right, I'm going to go back to the articulations now, and here are 27 of a list of about 80, and I got these by looking at journals that deal with material science and deal with the environment and sustainability and that kind of thing. And here are the ones I had before: biopolymers, carbon taxes, design for recycling, but there's lots more. And we'll just look at a few of them. Well, what can you get out of this? If you look at them, each one has a prime objective, something it's really trying to achieve. For instance, domestic solar PV is designed to reduce dependence on hydrocarbon fuels by generating electricity from the panels on your roof, that kind of thing. So that has a prime objective, but it also has other dimensions: economic, legal, and all the rest that I mentioned. So if we just list the main features that come out of a collection and a bigger collection like that, we could isolate the following words. These are things that have to do with materials: biopolymers, desalination, ethical material sourcing, that sort of thing. Those have to do with the environment, material efficiency, design for reuse, and that sort of thing. These have to do with energy energy and materials are very closely linked. Electric cars, grid-scale energy storage, that kind of thing. These have to do with legislation, and there's lots of them. And furthermore, the amount of legislation increases every year. In Europe, we have EU directives, and if you open the paper, the business section of the paper, almost every week there's another EU directive. So there's regulation, and you can't avoid it. A development, an articulation which is illegal is not a sustainable articulation. There are things that have to do with us, human beings, social equity, investment in education, that sort of thing. So there's society. And finally, all of them have an economic dimension, so I'll put economics at the bottom. Well, you may wonder where that this is a rather arbitrary list. It's not completely so. It is arrived at from a distillation of what we've found from these. And it's not unlike that list that I started with on top of the transport picture. It's the same issues coming up yet again. Well, I'm going to put those onto a layer as well. You'll see why the layers in just a minute. And I'll make it a hexagonal layer like that. Here's materials, here's energy and environment, and here's legislation and regulations, and here's society and economics. And the idea of that is simply to remind us that those are things that we, in examining an articulation, we ought to look at these and at least ask ourselves, is there an energy problem? Is there a materials problem? Is there an environmental problem? Is there a legal problem? That sort of thing. Right, we can now begin to assemble all of that and begin to see if we can make a structure. I said a framework at the beginning, a framework for thinking about this stuff. So here it is. Here at the bottom, I'm not sure if you can read it, is our prime objective. This is our articulation. Prime objective, what's its motivation? How big is it? And how quickly has it got to get done? I should have mentioned that earlier. All these articulations have a scale, a physical scale, and they have a time scale. They have to have a physical scale. If they're tiny, they're not going to make a difference. So they've got to be big enough that they make a change. If they don't make a change, they're not really contributing to sustainability. And they have to have a time scale as well. If they take 100 years, none of us are going to be around to see them. By now, problems will have changed. By 100 years from now, problems will have changed so much, in any case, that this articulation is probably irrelevant. So there has to be a time scale. There has to be a motivation, a time scale, and a size scale. Now, once you've got that, you have the opportunity then to examine the stakeholders. Here they are. And within the stakeholder panel here, we can ask how the stakeholders interact and what are they worried about. Well, once we know what they're worried about, we can begin to look for facts that relate to those questions. Can we inform ourselves about the stakeholder concerns and about the articulation itself in general? Can we inform ourselves enough to begin to judge whether the stakeholders' concerns are justified or whether they can be refuted in some way? So that's layer number 3. And that can be researched in a completely objective way. If somebody says, are biopolymers a good idea, you can go and look up. You can find out if there's any legislation about them. You can find out what material consequences, what are they, what materials are involved, what materials do they compete with. You can find out how much energy it takes to make them and that sort of thing. So that's completely objective, something that can be done as a research project. I'm going to call that fact-finding. Then the next question, though, is much more difficult. What is the impact of these facts on the 3 capitals that we saw at the beginning? Because that's the bottom, nearly the bottom line, not quite, but very nearly the bottom line. We think of these as the 3 important capitals that measure how we live, and what we want to know is what the impact of this on that is going to be. And finally, if we've debated that, that is a subjective part of the whole structure because it depends on your values, on where you've come from, on your culture probably, that sort of thing. So it's not nearly as easy as just researching facts. Once you've had a reasoned debate about this, which becomes possible at least when you've got some facts to base it on, then you can make a final judgment about whether it is the thing at the bottom here is something you would call a sustainable development. Well, at that point is a good moment to sit back and reflect. Just think for a little bit. Maybe there are some issues that emerge from these facts which are a bit worrying about what their impact is on these capitals here. And if so, this is the moment to ask yourself or ourselves whether there's another way of achieving the prime objective that we had down here. Does it have to be done the way that we were planning to do it, or could we do it in a different way, or on a different time scale? Are we trying to go too fast? Right, I'm now going to, those are the ideas, and I'm now going to tell you a tiny bit about a database to support the fact-finding stage, and then give you a case study, an example. Well, I think I heard, I think you've got the CES educational software here, and this is a new database which runs in that system. And it's called the Sustainability Database, surprise, surprise. And it's got in it a materials database. Well, that's in the system already, you've seen that. It's got a database of energy and another one of power systems. So a database about wind power and solar power and so on, and things like the carbon footprint of solar power and the carbon footprint of nuclear power and of gas-fired power and coal-fired power stations and that sort of thing. And it's got a database of energy storage systems. You'll see a graph made with that in just a minute, but it's got the obvious things, batteries, things like pumped hydro and pumped gas systems, various other ways of storing energy. So it's about making and storing energy. It's got a database of regulation. Hasn't got a great deal of North American regulation at the moment, but that's what we're working on right now. But it's got a lot of EU, that's European legislation. And finally, it's got a big database of the nations of the world, and I'll show you a tiny bit of that. That has records for the 210 independent nations of the world, with information about their economy and their civil rights and their, a lot of other stuff, which you'll see in a minute. Now, these data tables, I'll call them, they're like little databases, are linked to each other, so that if you have a material and you want to know, and you know where it comes from, you can now look at the record of the country from which it comes. And some of you may have heard of the Dodd-Frank Act in the United States, for instance, which prohibits the use of materials that come from conflict nations, nations where conflicts are going on. Well, if you were going to make something that happened to involve, let's say, cobalt, it might be useful for you to know where cobalt comes from, because if your cobalt comes from a conflict nation, you can't use it in the United States. And that, if you're trying to manufacture something, that would be quite an important consideration. Now, similarly, materials are linked to energy, and they're linked to the legislation that relates to that energy. I'm just going to show you two bits of records, one from this data table and one from that data table, to show you the sort of content. But as I say, the database is available and it runs in the system you've got. Here is a record for cobalt. I mentioned cobalt, and it's got data for physical properties like density and mechanical properties like yield strength and that sort of thing, and thermal properties, electrical, environmental properties like embodied energy and CO2 footprint, and countries of origin. And the countries of origin bit is new, and it looks like that. It says how much, which countries does it come from. That's 98% of the world's cobalt. And what fraction, this is the tonnage, in most recent data is 2011. This is the tonnage from those countries. And what you see is that of the 93,000 tons of cobalt produced a year, more than half comes from one place, the Democratic Republic of the Congo. Well, I mentioned the problem a minute ago. If you wanted to use cobalt, and a lot of products do use cobalt, then you might like to know where your cobalt comes from, and if it comes from the Congo, where most of it does, is there a problem with that? So let's now go to the Congo. This record for cobalt is linked to the records for these nations, so you can go straight there. And Go to that one, and that is it's about a quarter of a record for a nation, the Congo in this case. It's got a map, it's got a map and it's got a flag just to identify it, and it's got things about population, and it's also got things about the three capitals that I mentioned earlier: human rights, like press freedom and UN Development Index, manufactured capital, like GDP per capita, how much do people earn there on average. That isn't listed there, but it does have the median wage and that sort of thing. And it's got information about natural capital and its use in that country, like the ecological footprint. I'm afraid I haven't got time to go into definitions of these, but in the software itself, if you click on the name, it gives you it's a link to a page which describes what that term means and where the data came from, its origins. So that's what it looks like. That's the sort of content. Now here's the case study. Let's just see if we can make use of that method to reach some conclusions. Now, I want to make it quite clear that, first of all, I'm going terribly fast, and the mission that I actually had when I started working on this was to produce a course which was a project-based course, an activity-based course in which a method was introduced, and then individuals who were taking the course then had an individual project or a group project with 5 or 6 students to look at an articulation of sustainable development and analyze it. Well, electric cars was one. There were a whole lot of others, like biopolymers was another, and wind turbines was another, and there are a whole lot more. So this is an example of something which would normally take a term or at least quite a lot of time. There would be adequate time to do the research, and I'm going to do it in 10 minutes, so it's going to go very quickly. Well, let's look at the problem. And we'll do it globally because while you can do it country by country, we've been talking in global terms till now, so I'll go on doing that. Globally, we produce 60 million cars a year now, right now. And they produce about 15% of all the CO2 that's produced in the world, so it's a lot. And that has led governments to wish to decarbonize road transport, to make road transport less carbon intensive, and they've done it in all kinds of ways, like taxing high-consuming cars and subsidizing things, and among the things they subsidize are fully electric cars. Well, our own government has a target of 10% electric, not hybrid, but electric cars by 2020. And the Obama administration has pretty much a similar statement. It amounts to almost exactly the same thing. One of our political parties, thankfully a small one, wants to have 100% electric cars by 2030. No gasoline-powered cars at all by 2030. And you'll see in a minute the fact that that really is a bit of a dream. So let's see if this one is practical. It doesn't sound an awful lot, does it? Well, by 2020, there won't be 60 million cars produced per year. Given the growth of car production in China and India, it will probably be about 80 million, just extrapolating from today's growth rate. So we're talking about 10% of 80 million. So we've got a prime objective. It's to decarbonize road transport, and we've got a time scale and a size scale. 10% of 80 million is 8 million, and 2020 is the date. So we've got exactly the combination we want: a prime objective, a size scale, and a time scale. Well, we need to know who the stakeholders are. You can think of a lot, and I'm not going to, if you look at this, you'll find even more, but some obvious ones are national and local governments, and the evidence of this is their subsidies and all the rest of it that they now offer, and their driving force is the carbon targets that they have agreed to meet, international agreements to reduce carbon. Car makers, well, primarily they're worried about sales. Battery makers, well, they can see a large market there, but there's a supply chain problem. If you are going to make that many cars with that many batteries, where are the ingredients going to come from? There's quite a few rather difficult elements in batteries. There's the labor unions, they want employment. There are the drivers' associations who represent you and me. drivers, and there are environmental campaigners who want to get cars off the road because they are polluting things. Well, we can make a stakeholder diagram. Here we are, something like that. Here is government. Government at the moment, in most Western countries at least, is trying to influence battery makers, subsidizing research on batteries. It's pressing car makers to make electric cars. It is subsidizing electric cars to help drivers buy them. Meanwhile, the green lobbyists are trying to persuade drivers that that's a good idea and pressing government even harder to make it happen, and so on. You can look at the relationships, and as I said earlier, the ones that are probably of the most important are the ones up here, and that means we're worried about carbon targets, we're worried about supply chain for batteries, and we're worried about other things like legislation possibly relating to cars. Well, now let's go to the next layer up. We've looked at the layer that has the stakeholders in, and we can ask, well, what can we learn here? Well, the things we're going to need to know about are batteries, the materials. At the moment, electric cars use lithium-ion batteries, and there's at least one difficult element in them. There's actually more. There's a lot more difficult elements in electric cars, but one of them is lithium. There is the environment. Does it really reduce the CO2 content release if you make electric cars? There's legislation, in particular relating to batteries. There are social worries. Drivers are worried particularly about range. Electric cars don't go far enough. And they are also worried, of course, about price. The electric cars are not cheap. Well, we need to research those. So here's electric cars. One of the things you need is what's called a bill of materials for the car if you want to look at the materials question there. And that, don't try to read it, that is a very paraphrased bill of materials, but it's got lithium in it for the batteries. It's also got neodymium in for the motors, and it's got other things like that. And they too are problems, but the one that we're worried about for the moment is lithium. Well, that's where this linked table, set of data tables comes in. Here's the battery. It's got lithium in it. Well, the battery part of the database is linked to the materials that are in that battery. So you can go from the battery to the materials. Once you've got to the materials, you can go from the materials to the countries from which that material comes. Find out about them. You can also ask what legislation bears on batteries or perhaps the use of that material. And then finally, you can ask if we've got batteries, the energy to charge them has got to come from somewhere. Where is the energy going to come from? And what is the carbon footprint of that energy? If we're worried about the carbon footprint of the car, we've got to worry about the carbon footprint of the energy that was used to charge the battery. So that's the kind of reasoning behind all this stuff. Well, let's look at batteries. The current choice for this car, the Nissan Leaf, is a lithium-ion battery. 8 million cars a year, we said, each with 7.3 kilograms of lithium. That's that much lithium. 58,400 tons of lithium per year to make the batteries, if you want to have 10% of electric cars by 2020. Here is the lithium production in 2011. Here we go. The world production is 34,000 tons in 2011. So the demand for lithium, if you want 10% electric cars, using today's technology, I mean, you have to allow for the fact that in the 7 years between now and 2020, technology will advance, but even so, lithium is used for other things besides batteries, and here we are asking for 160% of present world production, so it's a great deal. Well, that's not as worrying as it sounds. There's lots of lithium out there in the world. It just is that the rate of production at the moment is low compared with the demand that this would create. So it suggests that we need some infrastructure. We need some more manufacturing plant. Well, what about if lithium is a problem, maybe we could find other batteries. And there are plenty of other batteries, nickel metal hydride, nickel cadmium, even lead acid and others. And here is the specific energy, that's the energy density in batteries. We want batteries with a lot of energy per kilogram because batteries are heavy, they make the car heavy, And that means all by itself that you're using more energy to drag the batteries around. So you'd like the battery with the highest energy density. Well, that's a plot made with from the energy part of the database, but I don't want to overemphasize this database. All of the information I'm showing you can be found on the internet anyway. It is not necessary to have this database to do these projects. It can all be found quite readily on the internet. So you can find pictures like this one, not this one, but like it, which show the energy density of energy storage systems, and the yellow ones are batteries. Others are things like flywheels and compressed air and hydrogen and that kind of thing. Well, the battery with the highest energy density is a lithium-ion battery. That's why they use it. And it stores about 0.6 megajoules per kilogram. And I'm going to tell you a funny little rule of thumb right now, which is the energy to drive a small car at the axle, on average, is about 0.6 megajoules per kilometer. So that means that if you want to drive a car around with batteries, you've got to have a kilogram of battery for every kilometer of range. And that's a sort of a rule of, a sort of nice order of magnitude to have in your mind. If you're trying to work out how heavy is the electric car going to be, battery is a kilogram per kilometer. Well, here's gasoline way up there. Factor between those two is a factor of 75. That's a bit misleading. You've got the electric battery has got energy that you can extract with an efficiency of about 90%. Gasoline has got energy that you can extract into usable form with an efficiency of about 33%. So it's a little more complicated than 75, but even dividing that number by 3, you can see that gasoline is about 25 times lighter for the same energy as even the best batteries we've got. That's why electric cars only go 100 kilometers, because if you wanted them to go 500 kilometers, the battery would weigh half a ton, and it would cost you at today's prices about $50,000. So those are the challenges. They're not insurmountable, but you can see that they're there. Right, next thing, regulation. Well, there's tons of regulations about cars, and I've isolated just one in Europe. You are not allowed to send any batteries to landfill. It's forbidden. Well, at the moment, there is only the smallest infrastructure for recycling lithium-ion batteries. It barely exists. If you're not allowed to send 53,000 tons of lithium in lithium-ion batteries to landfill, you've got a bit of a problem. You've got to find another way of dealing with it, and the obvious way is to recycle it, but that recycling infrastructure does not yet exist. Well, will it decarbonize road transport? You charge the vehicle on the national grid. The carbon footprint of gas-fired power, an efficient gas-fired power station, is 140, roughly speaking, 140 grams per megajoule of energy delivered. That's at the plug in your house. I just mentioned the delivered energy to propel a small car is about 0.6 megajoules per kilometer. And an efficient battery motor set will convert the energy in the battery to motion to power at the wheel with an efficiency, I think, of about 85%. I've had difficulty getting that number, but I think it's quite high. It's of order 85%, I think. So if you multiply those together, you get how much carbon it takes you to make your car go along. And it's 100 grams per kilometer on this basis. Well, at the moment, there are something like, in Europe, I think 28 or 30 small cars that already can propel you with a carbon emission of 100 grams per kilometer or better. So 100 grams per kilometer is not very good. If this were a coal-fired power station, it would be much worse. Of course, if it were a nuclear-powered power station, as in France, or if it was a hydroelectric-powered power station, as in Norway, this picture would change completely, and this number would now become very attractive because you're drawing the power from a low carbon source. But in Britain, that's the current value of our power, and that is the consequence. Well, there's no magic in that. That's a sort of unavoidable conclusion. That's how it works out. Right, we can now go to the next layer up and ask how these things impact on the three capitals. Remember, we've got these layers and we're working from one to the next to the next. Well, I'm going to paraphrase again. I'm compressing what's really a term's activity into 15 minutes. Natural capital. Well, the objective is simply not achieved. We are not decarbonizing road transport, at least we aren't in Britain. It would be possible if we decarbonized the grid, and we're trying to do that, but we're not going to do it in 7 years. So by 2020, that won't have happened. Manufactured and financial capital. Well, the supply chain for lithium is the problem that we saw. That can be overcome by expanding lithium production, and that could happen in 7 years. Quite a good example are rare earths right now that hit a peak of price 3 years ago, about $100 a kilogram, after being about $40 a kilogram. I'm sorry, about $1,000 a kilogram. It went up by a factor of over 10 in a short period of time because of shortage of supply, most of it coming from China. It took about 2.5 years for Australia and America to increase the production of neodymium to bring that price back down again, and it is now back down again. So material supply chain problems are not insurmountable. In fact, the timescale for doing something about them seems to be about 3 years. It takes about that long to get new plant online and generate more material. So it's not insurmountable. Human and social capital, well, there was the range anxiety, and I gave you the reason. It's because batteries are so heavy that if you put in enough battery to take you the sort of distance that cars normally go, then the battery would be very heavy. Right, we're getting there. Last step of all. Are we going to say this is sustainable development? And I think we have to conclude that in the time scale that our government mentioned, 7 years, it simply is not a sustainable development. It can't be done because the infrastructure is not there. On a 25-year time base, it probably could, because there would be time to establish a recycling infrastructure for lithium and a supply chain. Well, first the supply chain and then the recycling, because the recycling replaces some of the supply chain. It puts recycled stuff back in, but only when the car is worn out, and that isn't in 7 years, that's in 15 years. So it's a good point at this point to sit back and ask, is there some other way that we could achieve all this? Well, there's been a lot of suggestions about that. One has, a lot of them center on car use. Are we so focused on a car that we insist it does 500 kilometers on a tank full of gas, and it's got to be the size of a family car? Or could we envisage some part of the car use which uses little cars that only ever go more than 20 miles or 30 miles? Well, Paris has a car hire system which works very like that. There are electric cars all over Paris. You put your card in a slot, take the electric car, drive it around for a day, plug it back into another electric slot. The average distance that they go apparently is about 15 to 20 kilometers, and the recharging system is all there, so it's all ready to go. It's a different way of using cars. And you could imagine companies that have a large workforce providing electric cars and having charging facilities on premises so that they were only used to commute to their company and not for any other purpose at all, just for commuting. So there's that sort of thing. And then there's been the suggestion that if you're going to use electricity to charge things, maybe what you should do is not turn it into charging a battery, but rather use it to create, to make hydrocarbons, which you can. You can use electricity to make ethanol, for instance, from ammonia and that sort of thing. So there are other things you could think about, and that's the right moment to think about it. So the point about all this is not that you've entirely solved the problem, but we're now in a much better position to debate the question that was asked at the beginning, which is that is it possible to decarbonize road transport in 7 years decarbonize it by 10% in 7 years? And I think in this case, the answer has to be no, we can't. Right, the way that that has been used, we've trialled it at Urbana in the US, Barcelona in Spain, and in Cambridge. And we've done so by having groups of students at the master's level who were then divided up into groups of 5. And the idea was to introduce a project. We've got quite a number of them. The students in groups then investigate the stakeholders and discuss them, and then they come together and discuss the stakeholders as a class. The students, or the participants, I should rather say, then research one or another of those 6 facts that I had in the hexagon, and come together and discuss that and debate the impact of that on those 3 capitals, and then have some sort of final discussion like the one I just had, although more extended, about the nature of the sustainability of the project. Good. Well, that was rather a lot in a rather short space of time. I'll just tell you 1 or 2 of the people who have helped with it. There's my colleagues at Cambridge. We've been interacting with Carol Mulder in Delft, Peter Goodhue in Liverpool, who's a long-term educationalist, Alexander Vanna in Karlsruhe, Jordi Segolas and his class at UPC, that's in Barcelona, John Abelson and his students in Urbana, and finally I've had a lot of help from my colleagues at Granted Design, so I would just like to acknowledge them and thank them. Good, thank you very much.